Hello, my name is Sam McKennoch, and I have the privilege of leading the Allen Machine Learning Impact Team at Vulkan Inc. Thanks to the conference organizers for inviting me to this Applied Data Science talk. Today, I'll be talking on how my team uses machine learning to amplify scientific work in conservation and ocean health, with a specific focus on the scientific problem spaces. Scientists believe that we are in the midst of the sixth mass extinction, quoting from a paper from last year with the very happy title of Vertebrates on the Brink as Indicators of Biological Annihilation and the Sixth Mass Extinction. The authors find that every time a species vanishes, that the Earth's ability to maintain ecosystem services is degraded, and also that more than 400 vertebrate species have become extinct in the last 100 years. Normally, these extinctions would have taken up to 10,000 years in the normal course of evolution. While extinctions are on the rise, the body of scientific work also continues to grow at a near exponential rate. But with this growth, there are challenges that keep scientific work in all fields, including conservation, from reaching its full potential. Some of these challenges include exploding amounts of data, data silos, limits in funding and time, as well as accidental redundant efforts. Some of these challenges can be ameliorated with more compute power, but many are more complex than that and require deep partnership with scientists. Okay, now that I have your attention, let me tell you a little bit about Seattle-based Vulkan, which my team is a part of. Vulkan was founded by technologist and philanthropist Paul G. Allen. At Vulkan, we're committed to improving our planet and changing the trajectory of some of the world's most difficult problems by advancing scientific breakthroughs, developing technology tools and products for good, and empowering communities both locally and globally. We are one of a growing group of philanthropic conservation tech organizations. Work at Vulkan is wide-ranging and includes actions to support dam removals and protection of sensitive environments like Bristol Bay, which has the largest remaining sockeye salmon run in the world. My team is part of the Vulkan product department, and we support machine learning development within tools such as Skylight and Earth Ranger, which are large platforms used by many types of conservation stakeholders. For example, machine learning helps to identify where illegal fishing is taking place using a variety of input data types. Along with the rest of the Vulkan product group, my team, the Allen Machine Learning Impact Team, will transition from Vulkan to another part of the Allen family, the Allen Institute for AI, or AI2, in the fall of 2021. This move will combine world-class research, engineering, product resources, and talent to create greater positive impacts. My team, shown in the bottom right, is very excited to make this transition as we believe it will continue to help us amplify our work. Towards that, for the remainder of my talk, I'm going to focus on 3 case studies related to projects that my team is working on and which are in different stages of development. These case studies, while touching on the machine learning components, are meant to put a spotlight on our science partners and the need for more work of this type. For our first case study, we are partnering with Dr. Holly Fernbach and her team at Sea Life Response plus Rehab plus Research, or SR3 for short. They work to advance the health and welfare of marine life in the Pacific Northwest. Dr. Fernbach is their marine mammal research director and has an extensive background working with southern resident killer whales, also known as orcas. Southern resident killer whales are icons of the Pacific Northwest. You can see this image here shows K21 in front of the Seattle waterfront. They have a very urban distribution, and because of this, researchers have been able to study them for now almost half a century. Southern resident killer whales are an endangered population. They were listed as endangered in 2005, and there are only about 75 individuals remaining in the population. including approximately 1 new calf born in 2021. 3 key threats have been identified for the population: the contaminants, both in their food and water, impacts from vessels leading to both physical and acoustic disturbances, and declines in their prey abundance. Their primary prey is Chinook salmon, and they like to feed on not just any kind of Chinook, but really large Chinook salmon. So they are, in fact, picky eaters. So there's been a lot of concern over the impact of these declines in Chinook. A study published back in 2009 documented the link between Chinook salmon and southern resident killer whale survival. Specifically, that increased mortality followed years of declines of Chinook salmon abundance, a trend that continues into the present. And to address what kind of impact these declines had on southern resident killer whales and what kind of body condition they were in, SR3 started an aerial photogrammetry work back in 2008. Initial efforts in 2008 and 2013 used manned helicopters. In 2014, they moved into using drones to collect high-resolution aerial imagery. They were the first to pioneer the use of drones for research on free-ranging whales. SR3 can easily launch and retrieve their drones from their research vessels. It's very cost-effective and allows them to work in remote locations. And even more importantly, it's also very non-invasive research. The red arrow highlights the drone above the whales. They fly under a permit at an altitude typically greater than 100 feet. They can position their research vessel several hundred yards away, so the whales can get a health checkup without them even knowing anyone was there. And one of the first things they had to do was determine that these aerial images could be linked, largely via saddle patch pigmentation, to known individuals from boat-based images that have now been collected for census taking for more than 40 years by the Center for Whale Research in order to really understand long-term trends. Now turning to photogrammetry, the science of making measurements from photos like these high-resolution aerial images. This image shows you a couple examples of the type of measurements that can be taken: body length and condition profiles. All of the measurements that SR3 requires, all of the measurements that SR3 takes require dozens and dozens of measurements from each image to monitor the growth and assess the nutritional and reproductive status of the population. And when cetaceans lose condition, they lose fat behind the skull. When they have severe fat loss, that results in something called peanut head. This panel shows 3 adult female individuals. On the first, her eye patch angles outward, meaning she's in a very robust condition, and this is what we like to see. On the very right, you can see the eye patches are severely angled and there's a pronounced peanut head shape. She's lost almost all of her fat along that body axis. And so they developed a robust measurement called the eye patch ratio, which is a proportion of a measure that we take at the bottom of the eye patch to the top of the eye patch. The black line represents J35, while the gray lines are other individuals. When declines in condition are detected, SR3 provides management agencies with these qualitative health metrics as a sort of early warning system before whales die, to allow agencies to make decisions that can aid in the whale's recovery. SR3 is also able to monitor reproductive success. So southern resident killer whales have a very high rate of reproductive failure. SR3 identifies when individuals are pregnant to monitor their change in condition throughout the entire 17.5-month gestation. Using the example of individual J35 above, SR3 identified that she was pregnant and followed her from 5.5 months pregnant to right before she gave birth to her calf, J57, pictured on the right. Ultimately, SR3 does all this research to help inform conservation measures with the aim of recovering southern resident killer whale population. They provide these quantitative health metrics to management agencies towards identifying priority stocks that are really important for southern resident killer whales and identifying areas for potential vessel or fishery closures. And likewise, SR3 also identifies animals of concern so that in working with the Washington Department of Fish and Wildlife, more space can be provided for these whales so they can forage and get the nutrition that they need. But the amount of data collected is large. Thousands of images are generated per campaign, which takes months to analyze manually. With SR3, we at Vulcan really saw a great opportunity to be able to speed up the analysis and better connect it to adaptive management decisions. So for this project, we decided to test the feasibility of whether machine learning can accurately assess health metrics, simulating the workflow that SR3 already does, but with automating certain parts of it where applicable. And once feasibility is tested, then we wanted to deliver a semi-automated tool with an SR3 specific configuration targeted towards southern resident killer whales that could help them display the health metrics and get the data out. Additionally, we wanted to open source the platform itself in order to amplify our impact to other scientists. I want to help you visualize how a tool like this comes together. Instead of having a technology-driven approach, we took a user-centric approach, beginning with user interviews, trying to understand the different steps in their existing process. We asked them questions about every detail of their process in the search for pain points. This results in a journey map, a visualization of the process that a person goes through to accomplish a goal, which leads to a clickable prototype for user evaluation, and then we iterate on this multiple times. For our user research work here, we surfaced several pain points. Some had simple solutions like providing more data standardization and structure. In another case, we wanted to reduce oversight and training requirements by ensuring line measurement placement consistency between team members. We were able to do this by providing guidelines as an extension of the landmarks that the machine learning algorithms had previously automatically detected. We've just delivered version 1.0 of the aquatic mammal photogrammetry tool to SR3, which has already resulted in a time savings of 25% per image. Over a batch of images, the savings are even greater, currently going from as much as 6 months to approximately 6 weeks, and we are driving towards days as we continue to improve the tool. At a high level, there are two different pieces of the tool: a machine learning triage portion and a user measurement review portion. We created this two-phase approach for now in order to closely replicate SR3's workflow for analyzing images. For the machine learning component, we've started with a bare bones packaging in a Jupyter notebook. The user first uploads all the raw images they've taken from a drone flight. A mask RCNN network is used for orca detection, while a Siamese network is used for identification. Inference is run in these models in batch to generate orca detections and identities. An additional semantic segmentation network is trained to find landmarks within detected orcas, such as blowholes or eye patch locations. These landmarks are then used to determine whether an orca is in a measurable position for acquiring health metrics. The user steps through these machine learning results and verifies the machine learning generated suggestions, such as choosing the whale's identity from the top 5 suggestions based on saddle patch matches. Suggestions for orca identities are filtered further by applying constraints from the orca's social network and constraints from image sequencing. The reviewed results are then passed to the measurement review portion of the tool, built as a plugin in ImageJ, the tool that SR3 already uses to perform their measurements manually. The user can view and update metadata and reference points, such as the blowhole and the fluke notch, that were automatically populated from the machine learning portion of the tool. The tool also provides guides to make it easier for the user to draw those body condition lines all the way down the length of the animal based on the location of existing reference points. So, for example, the eye patch measurement requires 4 different landmarks to be identified in order to know where to draw that measurement. The tool removes the need to manually calculate where derived measurements should be located. For our second case study, we are partnering with 2 research specialists, Dr. Leah Sayeg and Dr. Franz Janssen at the Woods Hole Oceanographic Institute, or WHOI for short. Dr. Sayeg is a cetacean communication and behavior expert and has been studying the bottlenose dolphins in Sarasota Bay throughout her entire career. Among dolphins worldwide, about 25 to 50% of individual mortalities are estimated to have been caused by human behavior. As top predators, dolphins are also often considered sentinel species for ecosystem changes, since they will directly respond to factors affecting prey distributions, such as climate change and pollution, and thus they serve as an early indication of threats to ocean health. In collaboration with other researchers, Dr. Sayeg has established a large one-of-a-kind library of high-quality signature whistle recordings from most of the dolphins in this population. Signature whistles are used frequently by bottlenose dolphins when communicating and can be used to uniquely identify individuals. Using this data, it's been shown that dolphin calves practice whistling when young, eventually settling on a whistle typically like their mothers. The whistle is set within a few months after birth and remains the same for the rest of their lives. The data set in Sarasota Bay includes capture and release recordings in which individuals are known, as well as towed and passive hydrophone data. In part because we have access to a potentially large labeled data set over a long period of time, this population of dolphins in Sarasota Bay serves as the ideal group with which to develop and test machine learning augmented analysis of signature whistle repertoires. This project seeks to develop robust methods for detecting and classifying bottlenose dolphin signature whistles in order to track individual dolphin movements and changes in population by eavesdropping on their whistles. Ultimately, we hope to answer new questions about dolphin behavior and anthropogenic impacts. As with our first case study, we launched a user research process to better understand all the components of their work, from how they collect the recordings in the field to understanding what the ideal outcome from their annotated data would be. Through gaining a glimpse into WHOI's current workflow, we clarified the areas that are most challenging and prioritized our efforts accordingly. This work is ongoing and will help us understand how best to interface with existing tools. Over the past few months, we have shown that deep learning models can classify a subset of 20 individual dolphins based on the unique time frequency modulation in their signature whistles. We experimented with different frequency distributed CNNs. For now, using a basic CNN with an FFT type data augmentation, we achieve close to 90% accuracy on a labeled capture and release data set. Going forward, we'll be supporting the development of a database of more than 150 different bottlenose dolphin signature whistles, using this newly annotated data to train new algorithms to identify and automatically classify known dolphin signature whistles will be the next step. And then finally, developing and validating new open source tools that facilitate automated differentiation of signature whistles from other populations of dolphins worldwide. These efforts will enable efficient acoustic monitoring of dolphin populations, allowing researchers to monitor the aggregate effects of a variety of stressors from climate change to rapid marine developments, and thus contributing to critical conservation and monitoring efforts. For our final case study, entitled Soundscape of the Salish Sea, I'd like to share a new partnership we have with Senior Principal Oceanographer Dr. Kate Stafford and research scientist Dr. Manuel Castillo, who are affiliated with the University of Washington and the Cooperative Institute for Climate, Ocean, and Ecosystem Studies. The Institute is a partnership between multiple Northwest universities to foster collaborative, multidisciplinary research across ocean, atmosphere, and fishery science. To set the stage, consider what it's like to walk under a busy highway, and the sound is so loud you can't hear your own thoughts. That's what whales in the ocean experience, except instead of cars and trucks and ambulances, they hear the sounds of overhead ships, of oil and gas exploration, and of pile driving. Sounds that animals underwater can't just walk away from. They're constantly surrounded by noise, and that noise is increasing everywhere in the ocean. The image in this slide represents a 24-hour snapshot of underwater sound taken from the port of Anchorage, Alaska, where our partners recently did fieldwork. There are a variety of sounds, both human-made and natural, such as tidal currents, sea ice, wind, and waves, other marine mammals, and fish, which typically communicate at low frequencies. But animals also have to contend with everything humans do in the water, from small outboards to giant container ships. There are beluga calls here that are almost completely masked by the booming sounds of pile driving. Unlike light, which can't travel very far underwater, sound travels both further and more efficiently than it does even in air. And sound travels faster underwater than it does in air. And so, human sources of noise in the ocean, otherwise known as anthrophonic or anthropogenic sources, are very powerful, and they have the potential to interfere with animal communication and hearing because they can travel so far and so efficiently underwater. In the plot on the right, the blue line shows boundaries of the Stellwagen Bank National Marine Sanctuary near Cape Cod, along with vessel-induced sound and their ranges as they pass the area. The temporal overlap of signals has been shown to alter vocal behavior of marine mammals. For example, masking can disrupt mother-calf communication or migratory communication among animals that are widely spaced. In some instances, animals compensate for increased noise by changing their vocal behavior. They might change the pitch of the sounds that they make, or they might change how often they make sounds. In some instances, they might completely stop producing sounds. But overall, we know that increases in ship noise increases stress hormones in large whales. So a louder underwater environment is producing stressed out whales. Certainly as a human, we know this happens when we're in a room with a really loud fan and somebody turns off that fan. You didn't notice it before, but suddenly you can feel your shoulders drop and you feel more relaxed when the noise is lower. And not just marine fish and mammals, we've talked about use sound to navigate. Even coral larvae are sensitive to the auditory environment. Before management decisions can be made to try to limit the amount of sound to which animals can be subjected, we need to first understand what sources of sound could cause problems to wildlife and how wildlife is impacted by these different sources of sound. And to do this, we need to understand the soundscape, which is essentially a combination of all the sources of sound underwater. In addition to anthrophonic contributions, it's also wind and waves, geophonic, and other animals, biophonic. For our project, we are going to focus on understanding the soundscape of the Salish Sea, which is a well-studied and diverse area encompassing the water inlets around both Seattle and Vancouver, British Columbia. Everything from gooey ducks to Pacific giant octopus to king salmon to orca whales call this Salish Sea home. Now take a look at the ships that pass through this area over the course of just 1 year. Each one of those ships is putting noise into the water column, and all that noise and traffic can be a real threat to the animals trying to navigate down below. There exists an abundance of archived underwater acoustic data, as well as several networks of streamed hydrophone signals within the Salish Sea, but most of it has limited or no accessible pipeline for general signal extraction that the conservation community could build on. The ability to collect and archive acoustic data has far outpaced the ability to analyze the data in an efficient and robust manner to answer ecological questions for which acoustic data were intended. In our user research surveys, we found that scientists were spending more time sorting through data and not enough time focusing on the actual research towards conservation efforts. The spectrographic box here shows overlapping labeled sources of sound. To create this spectrographic box display, the authors manually separated sounds into 3 frequency bands, low, medium, and high. Each band was processed with different techniques to determine the sources of the sound and then was manually validated by experts. For our project, we are seeking to semi-automate this. Currently, there is no specific software or coding package dedicated to marine soundscape analysis other than custom code, normally in MATLAB or R, for specific tasks by different authors. We need a tool that can tease this information out. More specifically, our recent landscaping showed many soundscape analysis efforts towards airborne sound, for example, concerning West African elephants, frogs, and bird chirps, but much less existing effort on the marine side. We plan to leverage this recent work from airborne areas and bring the potential of machine learning into automating acoustic classification and detection with a human-in-the-loop option. Our tool will treat all sounds as signal and nothing as noise. It will be a standalone, but also be able to plug in with existing acoustic software packages, and it will play nice with data from existing hydrophone networks. The tool will have a dynamic architecture, allowing it to be configurable and retrainable by scientists with their own additional data and classes. This tool will help scientists quickly process hours of recordings and to reduce the time required for data mining, and gain back valuable time to interpret soundscapes, characterize contributors and their trends, and evaluate potential negative effects from anthrophonic sources in the ecosystem. We are attempting an all-inclusive approach as a pioneering effort in marine soundscapes, rather than bespoke methods currently available that are more marine mammal-centric. Together with APL, our partners, we hope to break new ground in this field. Now, to tie things together, I started by describing a world in a conservation crisis. Hopefully, I've been able to demonstrate through our project case studies that scientists working in conservation need help streamlining the analysis of their ever-growing mountains of data so that we can make a tight connection between data acquisition and conservation impact. For my team, we are hard at work creating user research-focused machine learning tools to allow these scientists to focus on what they do best. And with no clear market force in play for many aspects of conservation, and with limited government funding opportunities, it falls to philanthropic technology organizations like Vulcan and AI2 to fill in this gap. Thank you for your time, and I'm happy to take any questions you might have.
Thank you so much, Sam, for this fascinating talk, wonderful content, and great work. So I see we can go straight into the Q&A. I see a question came through on the chat, so please, others, keep typing your questions. This one is from a Yatam Abrahamson from Tobula, Tel Aviv. Sam, very interesting talk. Is this your goal to extend the area of the killer whale research? I guess whales are everywhere. Can you give a ballpark in dollar per square mile or kilometer needed to cover additional area in the research? Is it technically doable far away from shore? Sam?
Yeah, thank you for that question, and thanks for having me to give this talk. Yeah, so let's see. I want to be clear that the flying of the drones and the capturing of the data, that's all done by our partners, SR3, the scientists that have that expertise. On our side, we're really focused on the machine learning processing of the data after it's captured. That said, though, we're definitely interested in extending it to other species, other marine mammals. I might have mentioned minke and humpback whales. There are lots of whale populations all over the world. Not all of them are endangered, but they all have needs to be monitored in different ways. Some of the issues around that is permitting for groups to go on these boats and fly drones near conserved populations. If you want a ballpark, I think it's in the order of tens of thousands to do a drone campaign like this over a group of whales. In the case of southern residents, when they do this type of monitoring, it means that they've come into Puget Sound or the Salish Sea, and so they're within kind of a sort of fixed area. And we have a big group of scientists beyond this group that kind of keep track of where they are generally. If you're talking about on the open ocean, that's certainly a much more difficult task. But our partners SR3 do drone flights for other whale populations. Thank you.
Yes. So in your case study, Sam, you have contacted with science partners. The question come through as wondering whether or how you choose who to partner with. Can you talk a bit about that?
Yeah, sure. And that's a complicated question. We've kind of learned along the way. Some other groups in this similar space, things we've learned from them as well, including, maybe it's not the best idea to build custom tools that are very kind of tied in with one group's needs. And I agree with that, but I also, with an asterisk on that I think when you're kind of first engaging in an area, it's really important to have those deep partnerships and really kind of bespoke relationships. We're not experts in these areas. We really do want to partner and understand the needs out there. So not building custom tools, but building tools that are adapted to the scientists with an eye towards how we can have a broader impact in the future. So there's that, and then there's resourcing and technical alignment within the team and within the organization. If we wanted to do this, can we do it? And then I think something that's pretty unique about Vulcan and AI2, where we're going in a couple of weeks, is really that it's driven by team passion. So are there engineers, not just managers, but engineers on the team that are excited to work in this space, that they really connect with the conservation goals and the people working in this space, and that can hopefully really motivate them to do great work in this space in a way that they might not get in the commercial sector. Thanks.
Yep. Sam, you mentioned team passion. It's amazing that you named the team also as an impact team. So how do you measure whether a project is having intended conservation or ocean health impact?
So I think rule number one is to stay humble. it's impact means a lot of things. And again, we're not experts in these areas. We have to be willing to pivot as we iterate and the facts on the ground change. But generally speaking, you look at things like growth, how you can have more users for your tool or your platform. The users that you have, how do you get them to use the tool more often? And is the tool valuable for them? What kind of, for example, features could you add to make it more useful for them? So those things like growth usage value can be proxies for impact. In other cases, you can have specific metrics. Like for illegal fishing, you could have enforcement actions as a metric for impact. It's still kind of one step removed, but it's closer. People have come up with all sorts of things, like the shortest distance to saving a life, however you define that. So it's really kind of squishy, I would say. There's also like dollars per unit impact on an organizational level, the opportunity cost of if you do this project versus some other project. So really, to bring it back down, on my team, we really just focus in on partnering with scientists to understand on a deep level the conservation impact of the work they do and do our best to prioritize accordingly.
Mm-hmm. So a question came through the chat that any of these data sets publicly available?
Some of that, we have not specifically made them available. There are some data sets that we're using that are public. I think related to the Soundscapes project that will, as we shift into AI2 in the next coming weeks and months, we're really, that's one of our targeted goals, to make sure everything is visible to the external world as much as possible. So I would say stay tuned on that. We definitely have that philosophy to be open as much as possible.
Wonderful, wonderful news. We will definitely look forward to that. And perhaps just see if we have other questions, perhaps before we close, maybe to talk about the impact and then actually see through the work that gets used and implemented. I imagine that Vulcan in general would also partner with other types of partners as well, right? In addition to science partners, right? Could you just enlighten, comment a couple such or success, lesson learned in terms of other beyond the science partners as well?
Certainly, yeah. I mean, and that applies a little bit more to some of the products that I mentioned at the beginning of the talk, Earth Ranger and Skylight specifically, where they necessarily have to partner with government agencies a lot more. To that, we definitely talk with people, for example, at NOAA a lot. NOAA is the National Oceanographic and Atmospheric Administration in the US. So they, program heads, scientists, the whole gamut of things, technologists there, to align our efforts and make sure we're headed in the same direction. We have other people in the technology philanthropy space that we align with and learn from each other. WildMe is one that comes to mind at the moment. And yeah, other local government organizations. We have another new project with the Washington Department of Fish and Wildlife. So yeah, we're always open to new partnerships.
Fascinating work. And I actually, I see a question that's about it, the questions we have. Certainly encourage everybody to check out, they can just go to vulcan.com to check out the work. A lot of really fascinating work and great knowledge there as well. And thank you, Sam, for coming to KDD.
Certainly. Thank you for having me. Appreciate it.